Okay. So the important thing in file system, one of the most important thing is file system recovery, and which we'll see today. And the other thing which we are going to see that what happens in XV6 and what is XV6 file system all about. Now, you know that systems are prone to crashes. Now, suppose we take one example that a system call or anything intends to modify 4 blocks in the file system. So on disk, 4 blocks A, B, C, and D are going to be modified by some system call, where block A may correspond to file control block or inode block, metadata block. Block B may correspond to the directory, where the inode is it is the inode for the directory, and block C and D may correspond to the file data block. Fine. So there is a inode and then that particular block, and inside that inode there is another inode which is a directory, and inside that directory there may be 2 file data blocks. And a system call intends to modify these 4 blocks. Now what happens if system crashes after A and B are written? Now this is important. Suppose you have modified A, means metadata block, file control block. You have modified B, the directory structure, directory entry. But before you can modify C and D, the system crashes. Now, what is the after effect of this system crash? File system state becomes inconsistent. Block A indicates that there exists a directory entry for the file. Block B indicates that yeah, directory is there and the file should be present, but the file is not present. What can we do in such cases? Yeah. Any comments from anybody? Atharv, you understand the problem?
Yes, sir.
Bhavya? Bhavya
Yes,
Kaur,
sir.
you got the
Yes,
problem?
yes, sir.
Okay. Jatin Agrawal, Hiramba Jaiswal, Avasthi ji, Rachit Avasthi.
Sir, can you just repeat once more?
Okay. You could
Some
have
issue.
said it from yourself. Why I need to ask again and again? So you know that for every file there is a inode block. Fine. So inode
Yes.
block tells that whether this is a file or this is a directory. So this inode block may be having another inode block which is a directory. Okay. And that directory might be having some file whose data is there in C and D. Okay. And a system call is actually changing these 4 blocks. Might be creating a directory, and within directory might be creating a file. So these 4 things, 4 blocks are getting modified on disk. Now question here is, if system crashes after A and B are written, A and B are written correctly, fine. So what it indicates that because block A has been written correctly, it means it suggests that there is a directory entry for the file. Block B indicates that file should be present, but the file actually is not present because the data blocks cannot be written. Before data blocks can be written, system has been crashed. Now you understood, Rachit?
Yes, sir.
Okay. So what is required to be done in these cases? That's the question first up. It's clear that system crashes can cause inconsistencies on disk. For example, system may crash while creating a file. So there are options available in every operating system to check with the consistency. Fine. to deal with the inconsistencies. What you can do, you can scan all data on directory and compares with data in each block to determine the consistency. You can check the directory, you can check all the entries there, and then go and check whether there is a corresponding data block for every entry or not. Albeit it is slow, but yeah, it's a correct manner to do the things. Like if you see in Linux there is a utility FSCK, and in Windows there is check disk, which checks for inconsistencies and could potentially fix them also. Fine, could potentially fix them also. It's not sure that every time FS check or check disk can fix the inconsistencies, but yeah, they can try for that. As it is written here, disadvantages may not always be successful in repairing and may require human intervention. Means operator has to look, check the FSCK and see whether there any inconsistencies are there, and then delete the file, repeat the operations so that everything can be written again correctly. So it requires human intervention. What we want to do, we want to deal with these system crashes in an automatic manner. Fine, that you as a user or as a system administrator is not required to do anything, and inconsistencies can be corrected, fixed automatically. And this is how we do it. And these kind of file systems are known as journaling file system, which are based on log-based recovery technique. So when you invoke a system call, all changes, metadata changes are written sequentially to a log, and then system call returns. Log entries corresponding to a single uh, group of actions or single operation is called transactions. Now first everything would be written into a log, and then system call returns. Then entries in log are played. Played means are repeated. All those operations are repeated there in log sequentially to the actual file system structures. As changes are made to actual file system, a pointer is updated in log to record that okay, up till what point the actions have been completed. When an entire transaction is completed, the corresponding log entries are removed. Now, in between, if the system crashes and if log file has one or more entries, it means that OS has committed the operation, but file system is not updated. Then at the time of reboot of the system, after your system crashes and you reboot, your operating system checking the log can continue to play the entries fine as in step 3. So technique is very simple. Before writing into actual file system, you write into a log. And then from the log, you write into the actual file system sequentially, transaction by transaction. In between, if anything happens, your system is crashed. Next time when you reboot the system, you will check the log. If there are any entries which are there in the log, you will first of all play them onto the actual file system and then continue. In this way, you can always get the consistent file system state. How it works, let's see. In the hard disk only, in this disk only, a small portion can be reserved for a. Now suppose we take our own example that a system call modifies 4 blocks as before, A, B, C, and D, and this whole thing, this set of modifying this operation is known as transaction. Now what JFS ensures that either all 4 has to be done or nothing is to be done. JFS ensures that this transaction is done atomically. Either all 4 blocks are modified or none are modified. Because in between state that A and B are modified, C and D are not modified, it means that it is inconsistent. So what is going to be done? In the hard disk only, you reserve a space for log. First of all, do the operations. Fine. The metadata of these operations, ki kya karna hai, what is to be done, has to be written in log. Fine. As a transaction. And then from log, using the log, you play the entries from log to the actual file system. In between, if system crash is there, you can look at the log and ascertain whether we need to replay the entries or not. See here. Suppose copy the blocks to the log. Fine. First complete and then ABCD. So you write a bit that, okay, I want to write this into file system. Operating system is committing. Fine. So it is 0. This block will tell whether it is commit or not. And then write the blocks into write the blocks A, B, C, and D into the log. Set the complete bit in file system to 1. It means you are committing. So पहले complete 0 होगा, ABCD लिखा जाएगा log में, and then set the complete bit in file system to 1 means you are committing. Copy from log to the file system, actual file system. Set complete bit in file system to 0 and remove ABCD from the log. So these are the 4 steps. पहले log में लिखेंगे, fine. Complete bit को 0 करेंगे, fine. Set complete bit in file system to 1 means files operating system has committed, but still it is not written into the file system. Copy from log to the file system, whole transaction. Set complete bit in file system to 0 again and remove ABCD from the log. Now let's see if system crashes in between these steps. So what are the operations we need to perform? Copy blocks to log, first complete, then ABCD. This is the first step. Set complete bit in file system to 1. This is second step. Copy from log to file system, third step. Set complete bit in file system to 0 and remove ABCD from the log. This is the fourth step as before, as we have seen here. Suppose if system crashes during 1, suppose system crashes 1 or before 2. Fine. C is still 0. Ignore the transaction update. कुछ नहीं करना, कुछ हो ही नहीं पाया. If failure during 2 to 3, when you restart the system, fine, you find that C equal to 1, it means OS has committed. You proceed with 3 as usual. Suppose second step और third step के बीच में अगर system crash हुआ, तो log में क्या लिखा हुआ है? Complete as 1 means OS has committed, written into log, but still not updated into the file system. So what will you do? You just on restart, you'll find C equal to 1. Proceed with 3 as usual. If failure occurs during 3 or between 3 or 4, fine. If failure occurs during 3 or between 3 to 4, when you restart again, you will find C equal to 1, that it is committed but not completed. So you will redo 3 from the beginning. Suppose 3 और 4 के बीच में होता है कि A, B लिख गया, C, D नहीं लिखा. Fine. So you will redo 3 from the beginning. So this is how journaling file system work with the help of logging. Now, if you see carefully, directly operating system does not write into the hard disk. So if I ask you a question right now, if I want to update a file or I want to write something into a file, where I am going to write? Suppose I want to update a file, I'll go to the directory structure, traverse, and then write something into a file. So where actually I am writing? Any answers from anybody? Remember the previous lectures? Yes, Bhavya.
So you're writing to the temporary area or the logs, like you told.
Mm-hmm.
It
And in
doesn't
previous
have any.
lectures, what we have seen?
I don't think we covered this in the previous lecture.
No, we have covered two more things, if you remember carefully.
Well, it doesn't uses the normal file system. It can directly write to the disk, if that's what you mean.
No, no. Ultimately, the file is in the disk, so that disk copy of block has to be updated.
Yes,
But if you
sir.
remember carefully, that's why I'm reminding you, you people forget very easily. So we have seen two things: in-memory inode and buffer cache. Remember?
Oh, yes, sir.
So in-memory inode, which will get you, is the cache of inodes which are there on the disk. That in-memory inode. So if you want to traverse the whole thing, so there is one thing known as directory structure. You go from inode to inode to inode, going on traversing the directory structure, the tree, and finally you get the in-memory inode. That in-memory inode may direct you to the data block of the file, which is may be available in the buffer cache. So you will be writing into the buffer cache. And then later on, when that block is going to be replaced from buffer cache, then the actual disk block would be updated.
Yes, sir.
Everybody should understand this thing. Like you have done, your computer organization. Is processor directly accessing the main memory? Can processor access the main memory directly? Yeah, Tharv.
No, sir. Actually, it goes through L1 cache, L2 cache, and then
No,
RAM,
it,
and
it
after
cannot
that,
access L2 cache even.
yes, sir.
Processor is directly connected to the L1 cache only. So interaction is going to be there between processor and L1 cache. Now, if L1 cache thing is not available, then you need to bring those thing into L1 cache so that processor can access that. Processor cannot, because there is no connection between processor and L2 cache and main memory and hard disk. Are you getting my point or not?
Yes, sir.
So similarly, for the file system operation, so your accessibility, system accessibility is the buffer cache. Fine. There are two types of caches. One is in-memory inode. That is known as inode cache, so that you can quickly see the metadata of the file or directory and go through. And another thing is buffer cache, which is available there. So I'll tell you, please be with me and think carefully. When you want to open a file, so there are two possibilities. Please be with me, understand this carefully. You want to open a file, there are two possibilities. Either the file is already opened by another process, or file is already opened by another process and somebody is using it. File is already opened by yourself and right now you are not using it. You want to again open it. Or third, the file does. In these three cases, what will happen? Your directory, wherever you want to open a file, you need to go to that directory. That, okay, I want to create or open a file which is available in certain directory. So you to move to that directory, you do those change directory commands, cd, yes or no?
Yes, sir.
When you do cd, actually you are trying to give a path. Fine. So path is what? Every directory is also a file which is having a inode. So you go to one directory, then see the inode. Okay, I need to go to the another directory because in path another directory is there. You see the parent directory inode, you get the entry. See the another inode. From another inode, you see another entry. Are you getting my point or not?
Yes.
Fine. So direct inode by inode you'd be moving. And all these inode have to be there in the cache. If not, then these inode have to be brought back from hard disk to the main memory. So because you are going to deal with in-memory inode copies only. Now finally, when you reach to the file, you try to open it. If file has already been opened before, that particular inode will be copied again into the inode cache. You deal with that thing. And that inode finally will get you the data block of the file. Now, when you are trying to write into this file, those data block has to be brought back into the buffer cache if they are not there. So you are actually going to write into buffer cache. So buffer cache, you keep on writing. Everything is happening in memory right now. Means nothing is happening in hard disk. Now, when you update any data block which is there in the buffer cache, you mark that particular block as dirty. कि ये जब से आया है, उसके बाद आने के बाद it is dirty, means somebody has changed that. So you include a flag with data block in buffer cache as dirty flag. Bhavi, you know about cache replacement policies? Because cache is going to be small, you need to replace the cache. Which
Not
policies you know?
not very well, sir. But yeah, I've heard about them.
So because suppose having buffer cache is having only 100 blocks. So at any given time, all those 100 blocks might be occupied. And if you want to bring another block from the hard disk, you need to make space in the cache. So you need to do replacement of cache. So there are different policies, cache replacement policies. The most popular one is LRU, least recently used.
Oh yes, sir. Yeah, I've heard about
Fine.
them.
So what do? You keep on writing the file, you keep on updating the data blocks in buffer cache. Mind you, bacha log. Still, when you are writing something into buffer cache, copy of the data block, still the disk blocks are not getting updated. But when you update certain block in buffer cache, that particular block is tick marked as dirty. Later on, when there is a need to replace that dirty block, you update the डिस्क ब्लॉक ऑल्सो, क्योंकि जब तक वो डेटा ब्लॉक बफर कैश में है, किसी को भी वो डेटा ब्लॉक चाहिए होगा तो डिस्क तक जाने का जरूरत ही नहीं। जब उस डेटा ब्लॉक को बफर कैश से अपन हटाएंगे, तब हम डिस्क की कॉपी को, डिस्क ब्लॉक कॉपी को अपडेट करेंगे, तब तुम्हारा डिवाइस ड्राइवर आएगा मार्केट में। Then buffer cache will contact to device driver will contact to disk controller will use the disk algorithms we have seen, clook, scan and all. The logical address of disk is going to be converted into three-dimensional address, that cylinder number, track number, sector number, and the particular disk block. Should I explain it again? Athar, should I explain it again?
Sir, I got that. Sure about that.
Okay, now, because these things I have covered in the previous lecture, you people haven't understood it seems. Now there is another thing which is coming into picture, that is log. So you write everything into log, then replay the log. The log replaying would be done into buffer cache. Then later on from buffer cache, if you want to replace the data block, you update the disk block. This is the whole hierarchy of operation. Any questions from anybody at this point of time? Yeah, Avasti ji, clear?
Yeah, yes, sir. I got this.
Shreyas Tandon,
Yes, sir.
clear?
Yes, sir.
Okay. Okay. So let's move ahead. Let's move ahead.
Excuse me, sir.
Huh?
Sir, actually, I had a doubt.
Mm-hmm.
What if the system is crashing due to that file, means the particular file which we are trying to copy or whatever modify?
Okay.
It is a faulty file, and due to it, system is crashing continuously, and we are again logging into it every time the system reboots.
System is crashing due to a faulty file. Now, how come this particular thing comes in your mind? Have you ever experienced these kind of things?
Actually, I have seen some systems that just don't start up ever.
Mm-hmm.
Thought how it can happen, and now, as you were explaining, something clicked in my mind that this can
Okay.
happen.
Okay. Okay. Actually, file is not faulty. What is happening generally, that after usage, your file system on the disk, the pointers and all those, because there is a issue like fragmentation, fine, and then there is a issue like bad sectors and bad blocks, fine? Because it's a mechanical device. The magnetic disk is rotating and then head is touching those platters. So due to aberration, some blocks become, and then if there are more number of blocks which are faulty or which are bad sectors, then your system may crash again and again. So that particular file might want to write into those blocks, fine, which are already bad. So that's why you get again and again system crash. I don't know whether I have answered your question fully or not, because I didn't understood your question.
It's okay, sir. I got the gist of that.
Okay. 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 Now, Any other doubt from anybody? Okay. So let's see the file system, XV6 file system. This is organized in 6 layers. Fine. The lowest layer is buffer cache. Lowest layer is buffer cache. Fine. It actually reads, writes blocks on disk. So you can see here, I haven't, miss in XV6, after buffer cache will come that device driver thing. So though we are talking about file system, which is for the disk, see here, the lowest layer is buffer cache, which is in main memory, Lowest layer reads, writes blocks on disk through the buffer cache. So first you write into buffer cache and from buffer cache to disk. Second layer, fine, is logging layer, where you write into log. Second layer allows higher layers to wrap updates to several blocks in a transaction, which is to ensure blocks are updated atomically. Third layer is where you assign inode blocks to the files. Third layer provides unnamed files, each represented using an information node inode and a sequence of blocks holding the file's data. Fourth layer is your directory structure. As you know, directories are also a special type of files and which are implemented by inodes only. The content of directory is sequence of directory entries and then contains a name and reference to named files inode. So that to those directory entries would be actually pointed to the inodes, which are file inodes. So first layer is buffer cache, then your log layer, then inode and block allocator, then your directory structure. Fifth layer is your path lookup. How do you actually traverse through the path? Fine. So fifth layer, hierarchical path names, and you need to do the lookup of that. And then sixth layer, final layer is in Unix. If you talk about Linux or Unix, everything is a file. Device is a file, printer is a file, keyboard is a file, pipe, you have already seen a special kind of file, normal files. So this is the layer which implements the system calls. Fine. To give direction to the file system. You might have seen open system call, closed system call, and dupe system call, and all those system calls. So that this is implementation of those system calls. And above that also is not shown, that is your user interface, where you use system call library routine. Above that, you can use stdio.h functions, fopen, fclose, fwrite. So if you are using input output in C using fopen, that would be using a library routine open, and then that library routine open system call will be using sys_open at system call level. So understand, if you are using fopen in your C program, that f will be using the open system call from the system call library routine. That open system call library routine function will be using actual system call sys_open, which is implemented here. So the system call uses file descriptor. Bhavi, what is file descriptor?
Sir, it is a pointer to a file.
No. Atharv, I can't hear you. There is some issue in your mic. Huh? Some static noise is there. Avasthi, what is file descriptor?
Or it is some abstract pointer, abstract indicator types like that is used to open a
थोड़ा अपनी
file.
अपनी स्मरण शक्ति पे जोर डालिए. मैंने आपको कुछ बताया था. System wide open file table and per process open file table. कुछ ध्यान आया भव्य?
Yes, sir.
So file descriptor is an index to per process file table.
Okay, sir.
Remember the previous lecture? So when a file is open, there is a system-wide open file table which holds the reference count, that how many processes are trying to open this file. And there is a per process open file table which is just an array of pointer. Remember, struct file, array of pointer, fine, and that index of that array is your file descriptor. Got the point?
Yes, sir.
Okay, sir. Yes, sir.
Okay, so system call actually uses this file descriptor as a reference. And this file descriptor FD is like in pipe. Remember in previous lecture, I have explained you the concept of pipe where two file descriptors are written, FD1 and FD2. And using those file descriptor, actually system call can play with the file. So entry to the file, the reference to the file, फाइल से अगर बात करना है, फाइल में कुछ अगर चेंज करना है, you need to get the file descriptor. Without getting the file descriptor, you cannot get an index into a per process file table. In per process file table, there is a pointer to the system wide file table. In system wide file table, there is a pointer to the inode of that file. Inode which? In memory inode of that file, and in memory inode file will give you pointer to the data block of the file, and data block of the file are present in buffer cache. समझ में आ रहा है बच्चा लोग? भाई ये बहुत पूछा जाता है इसलिए समझा रहा हूं. ठीक? Linux file system is the most asked thing in technical interviews if you are going to companies which are working in systems. So you get as a user or as a as a system programmer, you get file descriptor. File descriptor is indexed into that array of pointers. That array of pointer actually point to system wide file table. In system wide file table, you get a pointer to the or in memory inode. In memory inode will get you a pointer to data blocks, and that data block is available in the buffer cache. So this is the whole path to deal with any file. Any doubts? Bhavya?
Not up till this point.
Okay. Rachit, you got the point? What is file descriptor?
Yeah, yes, sir. Yes,
Okay.
sir.
Okay. You can go through the previous lecture. I have explained it very clearly what is file descriptor. Okay. So system call use file descriptor, path names. We need to have recursive lookup, directory, inodes. You need to traverse one by one. Files, inode and block locator, then logging, transaction, and then blocks are in there in buffer cache. So this is the whole layer wise file system. This is how XV6 on disk file system structure look like. Fine. XV6 divides the disk into several sections. As we have already seen, what is boot sector, where you have the bootloader. So block 0 holds the bootloader, it's a boot sector. Block 1 is your super block. It contains metadata about the whole file system. The file system size in blocks, the number of data blocks, the number of inode, the number of blocks in the log. Fine. So block 1 is super block. Then from block 2 to certain blocks, there are number of inodes. Fine. So बॉस इसके बाद जितना ब्लॉक होगा ये सब inode होंगे, ठीक है, जो assign होंगे जब आप फाइल क्रिएट करेंगे. inode क्रिएट नहीं होता है, inode हमेशा assign होता है. So it means you can see that the number of inodes which are actually created when you are formatting your hard disk with a certain file system are actually going to limit the number of files also in your system. Number of files or directories. After inode array, there is a bitmap block. And bitmap block क्या होता है? It is just a map that which data blocks are actually occupied, which data block are vacant. So boot block, super block, inode array, bitmap to locate where are the vacant blocks and where are the used block, then your data blocks, and then your log. So this is how the whole disk is formatted in XV6. XV6 code for file system. You can go and see that code that is available on code here. Super block is at line number 3914 to 3919. You can see here super block, size of file system in blocks, number of data blocks, number of inodes, and number of log blocks. Fine. Inode array is line number 3926 to 3923. Type of file, device number, कौन सा disk है, कौन सा file system है, number of links to inode in the file system, size of file bytes, and then so any file which is getting created will use this struct d inode for creation. So inode can be read through this code. Superblock can be accessed through this code. Buffer cache. Buffer cache is nothing but a doubly linked list of buffers. This data structure struct buff is available at line number 3750. It is basic unit of storing a block's content in XV6 kernel. Consists of 512 bytes of data, device, and sector numbers pointed to the previous and next buffers, and then set of flags, which I was telling you, the valid, dirty, busy. The particular block is valid, particular block is dirty, particular block is busy, getting utilized by somebody else. These flags are available in line number 3759. You can see struct flag, in flags, device number, sector number, fine, pointed to the previous buffer, pointed to the next buffer, and then disk queue. So this is your buffer cache. It's just a doubly linked list of buffers. Now we need to see the file system from bottom to top. So I've shown you the buffer cache, but buffer cache is going to deal with the device driver. So we will be seeing the code for device driver first. So let me open the code also. Just 2 minutes. Yes. Fine. So buffer cache, because buffer cache is going to deal with the device driver, so we'll start the code traversal of XV6 from the device driver. That's what we are going to do. So the disk driver in XV6 is initialized in function IDE init line number 4151. Fine. Let's see line number 4151. 4151. So this is the function. Can you see it, or should I maximize it? Now can you see it? Bhavdi?
Yes, sir. Yes, sir.
Okay. So this is 4151, your function which deals with the device driver. This interacts with the device driver. Don't worry about these numbers. I'll be telling you. Don't worry. This function enables interrupts on last CPU, waits for the disk to be ready. Also check if second disk is present. There's a list IDE queue is a queue of requests pending for the disk, which is protected by IDE lock. So can we see the IDE queue here? Init lock, IDE, fine. And it is checking whether the disk 1 is present or not. Fine. And a queue is there. So what is going to happen? Let me explain it. Buffer cache, when there is a need to write the data back into the disk, will make a request to the device driver. And device driver in turn will make a request to the disk controller. And when a certain block is getting written, that particular block is going to be locked. Otherwise, another fellow can utilize that lock. So obviously there would be many requests. If you imagine a whole big system, there would be many requests from buffer cache to write the blocks into hard disk. These requests are known as, and at a time only one request can be serviced. And as you know, disk is the slowest device. So the time difference, time difference between the processor and disk is very huge. So buffer cache may generate request very fast, but disk may write it slowly. So obviously there would be a queue of pending request. Fine. And that queue is serviced one by one. Fine. And that queue, particular queue, is locked by ID lock so that no other process can do that. Function IDREW, IDE RW, line number 4254 is entry point to the device driver, which gets requests from the buffer cache file system. Its job is to sync a specified buffer with the disk. Fine. So let us see IDE RW line 4254. Fine. So you can see this is IDREW, which is working on struct buff. That struct buff is nothing but a pointer to the buffer cache, block of the buffer cache. So the argument to this is the block of the buffer cache. Now it is checking the flags, whether it is busy, valid, or dirty, or if the disk is not present and something like that. Fine. So this is the queue I was talking about, which is protected by lock. Acquire the ID lock and insert into queue or take the item from the queue. And then finally, after doing everything, everything, you can release the ID lock. So this is the queue which a process can lock while playing with the queue and release while it is done with the queue. So this is how this function ID RW work. I'll tell you the meaning of everything. So if you see function ID RW, this is typo. If the buffer is dirty, I told you, means somebody has written it, must be written to the disk. After which the dirty flag must be cleared and valid flag must be set. If the buffer is not dirty and not valid, it means कोई पढ़ना चाहता है, ठीक है, और वो चीज अवेलेबल नहीं है, indicates a read request. Buffer is not dirty but not valid. It means somebody wants to read something which is not there in the buffer cache. So you need to read the specified block into the buffer from the disk and valid flag is set. I want to read something that is not present in buffer cache. I will allocate a block in buffer cache or set of block in buffer cache. And when I allocate a set of block in buffer cache, I'll set those block as not valid. नहीं तो कोई दूसरा लिखना शुरू कर देगा उसमें, कोई और allocate कर लेगा not valid. Then read the data from hard disk and set the valid flag after. If the buffer is valid and not dirty, then there is nothing to do. Now, this function ID RW does not always send request to the disk. This may be busy. Actually, I told you to add a request to a queue. If this is the first request in the queue, then it starts the requested operation and blocks until the completion. Actually, what is happening is not only in XV6. What is happening, because system is dealing with the buffer cache all the time. So the disk copy and the buffer cache copy of the blocks are out of sync. Now what system keeps on doing using these dirty, busy and valid flags? This is the duty of system to make disk copies, blocks there in the disk, the copy of the blocks there in the disk, and the buffer cache blocks sync with each other. Means both should be having same data. Both should be having no inconsistencies in between. And this is what is getting done, you can say, out of band. Why I'm saying out of band? Because it's not like कि जब buffer cache में लिखा उसी समय disk में लिखा. That particular policy is known as write through policy. You change the buffer cache, then you at that point only you change the disk copy also. So in XV6 that write through policy is not getting utilized. XV6 is writing into buffer cache, and then these buffer cache, the system will these two functions ID init and ID RW to slowly and gradually and eventually make the buffer cache and disk block copies consistent. This is what is getting done. Okay. Now buffer cache code. This code can be found in sheet 43 and 44. The buffer cache is initialized at the startup in the main function and used to cache disk content. We know that. To read a disk block, there is a function known as bread at line number 4402. Let's see. 4402. So this is bread, which uses bget. Fine. So you want to read. Remember क्या बताया था अभी? ठीक है. So read करना है तो पहले block को invalid करेंगे. That's what we get, a block which is invalid. See the not here, and then we use bget, which will be actually getting you the device ID and the sector number. And finally, we'll be using this IDE read route RW function to read the things into the buffer cache. So that's what is explained here. To read a disk block, bread function is utilized. This function calls bget, as I've explained, looks for the particular sector in the buffer cache. If the given block is in cache already and not being used by anyone, then bget. This block may be clean valid or dirty valid. Someone else got it from disk and maybe even wrote to it, but it's not using it. Then no problem, fine. क्योंकि तुमको लिखना है और recent writing उसमें available है, you can read it. You want to read it only, and recent whatever has been done on that block is there because the block status is valid. Even if it is dirty valid, you know that somebody might have written it, you just want to read it. Fine. If it is valid, you can, and block is available in the cache. Fine. Then bget can return that. If it is in cache but busy, हो सकता है, देखा ना एक busy flag भी है, cache में है but busy है means that block is getting utilized by another process. Then bget sleeps on it. After waking up, tries to lock it once again by checking if the buffer corresponding to that sector number exists in cache. ठीक है, तो क्या करेगा, बी रीड कॉल करेगा, वो bget को कॉल करेगा, bget अपना सेक्टर नंबर चेक करेगा कि बफर कैश में है कि नहीं. अगर वो है और बिजी नहीं है तो रिटर्न हो जाएगा. अगर है बट बिजी है तो bget would be doing the busy waiting on it, sleeps on it. Possibilities: if the sector number is not in cache, that is important. If the sector number which you want to read is not in cache, then it must be fetched from disk. For this, buffer cache needs a free slot. अब वो एंड ऑफ लिस्ट से शुरू करेगा क्योंकि जो लीस्ट रिसेंटली यूज होगा वो सबसे पहले होगा. जो तुरंत अभी इस्तेमाल हुआ होगा वो सबसे पहले होगा लिस्ट के. दिस इज व्हाट इज द पॉलिसी. इट्स ए, आई टोल्ड यू, इट्स ए doubly linked list. Fine. So whatever the block which is recently utilized will be at the front of the list. The least recently used blocks would be at the back of the list. It start looking from end of the list. जैसे ही उसको finds a clean non-busy buffer to recycle, उसको मिलेगा. It allots it for this block, marks it as invalid. जैसे ही invalid mark करना जरूरी है क्योंकि इसमें ये busy हो गया, अब इसको हमको लिखना है. Since the contents are of another block and returns it. So when bread gets a buffer from cache that is not valid, it will proceed to read from the disk. Fine. bread के 3 possibilities हैं. मिल गया, somebody is speaking, Alok Ranjan. What are the possibilities for bget? मिल गया, कोई नहीं यूज कर रहा है, रिटर्न कर दो. मिल गया बट कोई यूज कर रहा है तो स्लीप ऑन इट. नहीं मिला तो किसी को रिप्लेस करना है. रिप्लेस करने से पहले उस ब्लॉक को, जिसको भी रिप्लेस करेंगे उसको देखेंगे वो डर्टी है कि क्लीन है, नॉन बिजी है. ठीक है, तो उसको इनवैलिड करेंगे. ठीक है, सिंस द कंटेंट आर ऑफ अनदर ब्लॉक. और फिर इस ब्लॉक में डिस्क से पढ़ लेंगे. दिस इज व्हाट इज द ऑपरेशन ऑफ bread. Processes that lock the buffer in cache may make changes to it. It must flush the changes to disk using bwrite before releasing the lock on the buffer. So B write function is at line 4404. We have seen B read. Now we see B write 4404. Oh, 4404. 4414. This is, sorry, I've given you the wrong number. The B write is at 4414. Fine. Again, is you can see using a IDE RW. So get the block, make the block. If you're busy, fine. You cannot make the flag dirty and then write it. So you are making flags as dirty and then writing the block into the disk. B write first mark the buffer as dirty. So the driver knows it's a write operation. Calls ID RW, which acts the request queue. I told you there is no guarantee that buffer will be immediately written. There may be another pending request in the queue. The process still holds the lock on the buffer as the busy flag is set. So no other process can access the buffer. तो दो ऑपरेशन अभी देख लिए, B read which uses B get and then B write which uses ID RW to write the block into the disk. When a process is done using a disk block, it calls B release. ये क्या करेगा? It will release the lock by clearing the busy flag. You can see that 4425. B release. Fine. It will release the clock. Fine. The function releases the lock by clearing the busy flag. Other processes might be sleeping on this block. Fine. Can start using this. This block contains again whether clean or dirty. This function also moves the block to the head of the buffer cache. इससे पता चलेगा कि ये अभी तुरंत यूज हुआ है और LRU replacement will not be able to replace it immediately. Fine. So when you are done with something, you will use B release to release that block. Fine. And ये जो किया ना हमने B next previous B previous और इसे पॉइंटर चेंज कर रहे हैं, क्या कर रहे हैं हम? B कैश हेड की तरफ ले जा रहे हैं, इस ब्लॉक को आगे की तरफ ले जा रहे हैं. ठीक है. और वेकअप कर दे रहे हैं जितनी भी प्रोसेस which are sleeping on this busy block so that they can again try for accessing this block. So 3 functions: B read which uses B get. B get has 3 options. Then B write which uses ID RW, and then B release which allows other process to access this block. Fine. Any questions? Any questions from anybody? Okay. Fine. Similarly, there is logging. Fine. And recovery. inode structure. Fine. File deletion. Read and write. So I have gone through in these slides from, you can see if this figure from bottom to up. So I've explained the buffer cache. Next is logging. Next inode and block allocator. Then the directory inode, recursive lookup, and file descriptors. Now what I want you to do, fine, I'll upload these slides which you are seeing right now. And then this particular code, fine, on Moodle. I want you to read the remaining slides by yourself and try to understand that. Fine. On Thursday, we'll be having a half an hour small, and then I'll complete this lecture. Any doubts? So I'll be uploading these two things, the code which is utilized in these slides. I've explained you up to buffer cache. Now you need to see logging, inode, path name, and system calls. So you'll be seeing it by yourself. Try to understand the code. On Thursday, we'll be having a small quiz of half an hour first, and then based on these slides only, based on this lecture only, based on this lecture, whatever is there, and obviously if it is based on this lecture, the previous lecture of file system will also are subsumed in this lecture, because the generic file system, whatever I have explained, is subsumed in this lecture. So you need to study file system, and then these slides, which I am not teaching you right now, and then there would be a small quiz on Thursday. Fine. First of all, half an hour, 1 hour, and then I'll complete this lecture. Any doubts? Bhav, any doubts?
Sir, how does buffer and log file or journal file interact with each other?
Yeah,
When
it
you're
is just
writing,
code. Fine. So it's like buffer is an incarnation, main memory. Buffer cache is main memory incarnation of your disk. Okay. So system does not feel that it is writing into disk. For system, buffer cache is the disk. Try to understand this.
no, I don't have issue with that. I mean, um, for example, you have written to a file, but basically you're first writing to a buffer cache.
No,
Then
no, no,
that
no,
buffer
no,
cache,
no, no, no. Please be with me. Please be with me. 1 minute. Fine. See here, भव्य यहां से शुरू हो रहा है सिस्टम कॉल से, ठीक?
yes, sir.
फाइल डिस्क्रिप्टर मिला, सिस्टम कॉल राइट वाइट किया,
Okay,
कहां पे
it's first
लिखना है,
writing to logging.
ये ठीक समझ में आया?
Okay.
ऊपर से चल रहा है, ठीक है? फिर डायरेक्टरी मिली, डायरेक्टरी से फाइल आइनोड मिला, ब्लॉक मिला, फिर लॉगिंग आया,
Yeah,
तो अपन
yes.
बफर कैश में बाद में लिख रहे हैं.
Acha, okay, okay.
So you are here. This is application, no? You are above system call. As a system designer or the programmer, you are above system call. So the interaction is like system calls, which will be using recursive lookup, which will be using directory inode, which will be using file inode, and then if you want to change something, do some metadata changes, you will be using the logging, and then buffer cache. जब logging में लिख लोगे, तब log से
So,
लिखोगे buffer cache में,
so
ठीक?
buffer cache is basically useful for reading data, not for writing data.
ना, we are writing into buffer cache only. हम सब कुछ कर रहे हैं बफर कैश में ही. हम
But
जो भी लिखना चाहते हैं, पढ़ना चाहते हैं, वो बफर कैश में ही कर रहे हैं.
but the logging file exists in the buffer cache or in the disk?
See, it is a separate partition in the disk.
Yes, sir.
ठीक है? So whatever you are trying to do, भाई अगर सिस्टम क्रैश करेगा, सुन मेरी बात बुद्धू, एकदम गधे हो सब लोग. सिस्टम क्रैश करेगा तो बचेगा क्या? बत्ती जाएगी तो डिस्क वाला बचेगा कि बफर कैश बचेगा?
Disk वाला.
तो पहले लॉग लिखेंगे ना, यहां डायरेक्ट लिखेंगे, समझे?
And then it will be synced with the buffer cache.
क्योंकि तुम परमानेंट स्टोरेज तो डिस्क है ना बच्चा.
That is what I'm trying to ask, meaning the buffer cache really doesn't do much for write operations, only for read operations. It only accelerates read operations.
नो लिसन, यहाँ पे ये 4 ब्लॉक जो थे, इनको तुम अपडेट कर रहा था, ठीक है?
Yes, sir.
अपन को क्या करना है, किस ब्लॉक पे करना है, ये सब अपन पहले लॉग में लिख देंगे डिस्क में, ठीक है?
Yes, sir.
ठीक है? एक काम हो गया कि लॉग में चला गया कि भाई ये करना है हमको। हम्म
Yes,
अब
sir.
जो लॉग में होगा वो सब रिप्ले करेंगे हम डेटा ब्लॉक में। हम्म
Yes, sir.
अब लॉग में जो रिप्ले करेंगे वो हम डिस्क में नहीं करेंगे, वो अपन बफर कैश में करेंगे।
Okay, okay.
फाइन, वो अपन बफर कैश में करेंगे। अच्छा, लॉग से रिप्ले करने में बफर कैश में अगर बत्ती चली गई तो क्या रहेगा? लॉग तो हमारे पास रहेगा ना, क्योंकि वो डिस्क पे लिखा हुआ
Yes,
है।
sir.
हम्म
No,
तो
but
अगली
it,
बार
I mean, it will really not accelerate the write operations because first you're going to the disk and
हम्म
then it's going to the buffer, right? So you will still be limited in a sense like you want to read suppose the same file maybe 20 times. So you can get that content directly from the buffer.
हम्म
It will bring a big difference because now you're reading from the main memory. But while you're trying to write something to a file 20 times, you first always have to go to the log file
अगेन
or the
गलत
log.
सोचा तुम।
Okay.
हम लॉग में क्या लिख रहे हैं ये नहीं लिख रहे हैं, हम लॉग में वो सब डेटा ब्लॉक नहीं लिख रहे हैं, ठीक है?
Yes, sir, I
हम
know that.
लॉग में केवल कहानी लिख रहे हैं,
Yeah,
ठीक है?
but the
कहानी का
thing is
मतलब क्या
the
हुआ? हम लॉग में सपोज मेरे को एक पूरी फाइल को क्रिएट करना है और वो फाइल 15 डेटा ब्लॉक को छेड़ेगी, मतलब चेंज करेगी, ठीक?
yes, sir.
तो तुम क्या सोच रहे हो, वो 15 डेटा ब्लॉक लिखेंगे लॉग में पहले? नो।
No, no, no. I know that you're not. But the thing is, the जो the what
आई विल राइट ए
the
समरी
first
ऑफ
response
ऑपरेशन।
time of the disk is so much higher than the memory. It's about 1,000 times higher than the main system memory. So you still basically are waiting for the response time or for random IOs. You're not waiting for sequential IOs. Even disks can reach the speeds of SSDs. I know that. So I was thinking in terms of the response time. It will go really down because you're directly writing to the log first.
But not do without that.
Yeah,
The
can do.
problem here is that you need to
Safety
write
issue.
something. Maybe you can have a log cache also, but that will not help you.
It won't help because it has to
Because
be written to the disk for
uh,
safety reasons.
so you and then you may ask me a question, sir, log में लिखते समय ही चला गया तो कुछ हुआ ही नहीं actually.
Yes, sir.
Okay, we haven't started the operation, so that's the issue. And log can be like a different kind of partition where you are not required to the file system. Yeah, you are right in your sense that in any case you need to write to a log, but that log is like a very small entry. Are you getting my point or not?
Yes,
लॉग
sir.
में
I
हम
know.
पूरा डेटा ब्लॉक नहीं लिख रहे हैं।
I know it's just a summary of it, but
इट्स जस्ट
like
वन लाइन कि इस पूरे
mm,
ट्रांजैक्शन में अपन को क्या क्या करना है। So there is a
yes, sir.
methodology, there is a way of writing into log also. That's a sign language kind of fine.
Yes, sir.
So you are just writing, but you are very right. Before doing any operation, you need to write into log. Fine. So you gain something, you lose something,
Yes, sir.
and that's why we are going towards SSDs and all those things nowadays.
Yeah, I've seen the random write operations are about 10 times slower or maybe 100 times slower than the random read operations
Mm-hmm.
because I believe they're not able to the buffer.
Mm-hmm. Mm-hmm. Because when you want to write it, there are two things. But when you want to read it, you just need to copy. If that is not available, more often than not that would be available because LRU is just what. Look, I don't know whether you have understood this particular thing or not. Uh, there is a term known as locality of reference.
Yes, sir, I know about it.
So when you have a cache, so generally this locality, temporal locality or spatial locality, uh, is going to be exhibited. Fine. So and you need to understand when we see the memory management, ठीक है? अभी अभी सभी लोग के लिए ये एक सोचने का बहुत अच्छा पॉइंट है। ध्यान से सुनिएगा। I want to run a program Fine. Big program, a big software. Maybe your the software which is bigger than your RAM size. So there is a huge game of say 12 GB and your RAM is 8 GB. Obviously, the whole software cannot come into main memory. अब देखिए प्रोसेस आता है हार्ड डिस्क से, ध्यान से सुनिए चीजों को. प्रोसेस आता है हार्ड डिस्क से, फाइल आता है हार्ड डिस्क से, and later on we'll see the memory management कि पेज आता है हार्ड डिस्क से, if you remember paging and all. So these are different layer of implementations. When you say I am running a process, remember there is a state in process state, Unix 9 state process model. If you remember, there is a wait suspend state, a process which we believe is going to wait, बहुत ज्यादा देर तक वेट करने वाले हैं. So why not suspend that process into hard disk using swap space? तो अपन प्रोसेस को भेज देते हैं हार्ड डिस्क में. दूसरे एस्पेक्ट में देखो यार, ये फाइल को हार्ड डिस्क में भेजा, कोई नहीं यूज कर रहा. तीसरे एस्पेक्ट में देखो, when we do paging, when we see memory management, you will be seeing we'll bring pages back into main memory. So actually आता क्या है, क्यों भावे?
Sir,
क्वेश्चन समझो.
I couldn't understand your question.
When you were running processes, there was ready queue.
Yes, sir.
There were states, no? In XV6 there were 5 states only.
Yeah.
It's blocked, ready, or what?
Yeah.
If you see Linux, or Unix, it's a 9-state process model. If ready queue, if queue is there, ready queue is there, a process is ready. If say 1,000 processes are ready to execute, you cannot have queue of infinite size. So in Unix there is a ready suspend state also. कि ready queue बहुत ज्यादा हो गया, भर गया, तो कुछ प्रोसेस को उठा के हार्ड डिस्क में डाल दिया.
Yeah, I know that.
और इसी तरह blocked queue, कुछ प्रोसेस को उठा के हार्ड डिस्क में
If it starts reaching it starts consuming so much memory, put it back to disk.
Because you know it is ready, but it is not going to get chance in the disk. So what you are exchanging in terms of processes from hard disk to main memory?
Yes,
in
sir.
file systems, what you are exchanging?
Pages.
In file system, no. You are exchanging files.
Oh, sorry. Yeah, we are exchanging files.
You are exchanging blocks of files.
Yes, sir. Blocks.
And when we will study memory management, which is our last topic, you'll see that we'll be seeing pages, that pages in hard disk and pages in main memory.
Yes,
So
sir.
what actually is getting exchanged from hard disk to main memory? The processes, the files.
No, the data is being exchanged.
So data is getting exchanged, no?
Yes, sir.
And the manifestation of that data is different in different module.
Yeah.
So this is a good thing. I don't know whether you people visualize this or not, that when you are copying process from hard disk to main memory, क्या वो file system use कर रहा है? और
Yeah,
क्या
it could be.
और क्या फाइल सिस्टम जब फाइल कॉपी कर रहा है, when it is copying file from hard disk to main memory or blocks from hard disk to main memory in buffer cache, whether it is using memory management?
They could be using each other.
So that's what is a nice question, things to ponder, because we every time we study these things in isolated manner.
Yes, sir. I understand. You're talking about the interactivity graph.
Yeah. how these modules are actually interacting. So at one level, you are saying when you are seeing processes, you seeing that processes are getting copied from hard disk to main memory. At another level in file system, you are saying no, disk blocks are coming into buffer cache. At another level, no, these are pages in hard disk which are coming into main memory.
Yeah, they're just data and different
So,
functions are
so which
manipulating them in a
abstraction
different
is
way.
getting utilized and which abstraction is using each other? That is the major question to understand. So let's stop here. I've already told you that what we are going to do on Thursday. There would be a small quiz, uh, half an hour. So I will be loading these two things just now in on Moodle, and be prepare file system chapter and the slides which I haven't taught you, and there will be some question on that in quiz. We'll be having a quiz, and then I'll complete this lecture. Thanks a lot. Thank you.
Thank you, sir.
You can leave. Thank you.